let's understand how a red-black tree works. A red-black tree is a special type of self-balancing binary search tree in which each node can be either red or black. The leaf nodes, commonly referred to as nil nodes, are considered black by default. Now, a red-black tree has 5 key properties that are essential for maintaining its balance. First, we have already discussed that every node are either red or black. Second, the root node should always be black. Next, the nil nodes are always black. Furthermore, if a node is red, both of its children must be black. This means that a red node cannot have a red child, which prevents 2 adjacent red nodes from existing in the tree. Lastly, every path from a node to its descendant nil nodes must contain the same number of black nodes, ensuring that the tree remains balanced in depth. For example, let's consider this node with value 5. If we follow the path to the leftmost leaf node, we find there is only 1 black node in that path. Now, if we follow the path to any other leaf node in the tree, there will also be exactly 1 black node along the way. This demonstrates that the property of having the same number of black nodes in every path from a node to its leaf nodes holds true in this tree. This balance is what ensures the efficiency of operations in red-black trees. Now, keeping this property in mind, it's quite apparent that the height of the tree should be at most twice the black height. The black height is defined as the number of black nodes between the root and any leaf node, not including the leaf itself. Since there can be alternating red and black nodes in any path, the total height of the tree can be no more than twice the black height. Additionally, the number of nodes in a red-black tree should be at least 2 to the power black height minus 1. This is because the black height represents the minimum number of black nodes along any path from the root to a leaf. In the best-case scenario, where every level alternates between red and black nodes, the tree can have the fewest possible nodes while still maintaining its balance. This lower bound ensures that even in the most compact arrangement, the tree has a significant number of nodes relative to its height. By solving these 2 equations, we can determine the maximum height of a red-black tree. The height can be no greater than 2 times the logarithm, base 2 of n plus 1. This means that as the number of nodes increases, the height of the tree grows logarithmically, ensuring that the tree remains balanced and efficient for operations like search, insertion, and deletion. Now, let's take a look at the code for the node class. We will begin by defining the class node, which will accept the data and color of the node as input parameters. The color will be set to red by default. In the init method, we initialize the data attribute with the provided value and set the color attribute to red, unless specified otherwise. Additionally, we will define left, right, and parent attributes, all of which are initialized to none. This structure allows us to easily navigate and manage the relationships between nodes in the red-black tree. Next, we define the red-black tree class. Then inside the constructor, we initialize a sentinel node, referred to as nil, which represents the leaf nodes in the tree. This nil node is of type node and is set to be black. By using this sentinel node, we can simplify the logic for operations like insertion and deletion, as all leaf nodes will point to this single nil node, making it easier to manage tree boundaries. We also initialize the root of the tree to point to this nil node initially, indicating that the tree is empty at the time of creation. In this class, we will later define methods for various operations, including insertion and deletion of nodes. These operations will utilize the properties of the red-black tree to maintain balance and ensure efficient performance. Now let's focus on rotations. For the moment, we'll set aside the node colors and concentrate solely on the mechanics of the rotations themselves. Let's see the left rotation first. The goal of a left rotation is to move the right child of a node up, making the node itself the left child of its previous right child. We will begin by defining the rotate left method, which takes a node as input, representing the node on which the rotation will be performed. First, we identify the node x and set y as the right child of x. Then, we shift y's left subtree to become the new right subtree of x. If y's left child exists and is not a nil node, we update its parent to x. After that, we link y's parent to x's parent. If x was the root node, we update the tree's root to y. If x was a left or right child of its parent, we update the parent's pointer to point to y. Finally, we move x to become the left child of y and set y as the parent of x. That was the left rotation. Similarly, the right rotation works in the opposite direction. We'll rotate the root node to the right and assign the right subtree of its left child to the node's left. The process is straightforward and mirrors the steps of the left rotation, just in reverse. Visualizing these rotations becomes even simpler when there's no complex subtree in the way. Just rotate the node in the respective direction and update the necessary pointers. Now imagine the tree forms a zigzag shape, like a right-left structure. In this case, we first need to perform a right rotation on the right child node. After that, we perform a left rotation on the top node to balance the tree. Keep these concepts in mind, as they will play a crucial role in the insertion and deletion operations. Now, let's move on to the insertion operation. The key idea here is that we initially set the color of the node to be inserted as red, so it doesn't violate the property of having the same number of black nodes along every path. If the tree is empty, the new node becomes the root, and its color is changed to black. If the parent of the inserted node is black, no properties are violated, and the tree remains balanced. However, if the parent node is red, this creates a violation of the no2 adjacent red nodes property. In such cases, we need to perform recoloring and rotations to restore balance and fix the violation. Now, let's visualize the insertion process. First, let's insert the node with the value 10. Since it's the first node, it becomes the root and is colored black. Next, we insert 5. It is placed in its correct position, following the rules of a binary search tree, with 5 as the left child of 10. Since the parent, 10, is black, there are no issues. Then we insert 15 on the right side of 10. Again, the parent is black, so everything remains balanced. Now, let's insert 3. This time, the parent node, 5, is red, which creates a violation of the red-black tree property that no two red nodes can be adjacent. When this violation occurs, we need to check certain cases. The first case is when the parent node is the left child of its parent, and the parent sibling, also known as the uncle, is red. When this happens, we recolor both the parent and the uncle to black, and change the grandparent's color to red. After that, we move upwards and repeat this process to ensure the tree remains balanced. In this case, since the uncle node is red, we recolor both the parent and the uncle to black and the grandparent to red. However, if the grandparent is the root node, we recolor it to black to maintain the red-black tree properties. Now, let's insert the node with the value 2. This insertion again violates the red-red property. However, this time, the uncle node is a nil node, which is considered black by default. Therefore, in this scenario, the uncle is black. This case is a bit more complex and requires both recoloring and rotations to restore the balance of the tree. If the inserted node is the right child of its parent, we begin by performing a left rotation on the parent node. After the rotation, we recolor the parent to black and the grandparent to red. Finally, we carry out a right rotation on the grandparent to correct the imbalance and restore the properties of the red-black tree. In our case, the inserted node is the left child of the parent, so the condition for the right child is false. Therefore, we proceed to recolor the parent node to black and the grandparent to red. Next, we perform a right rotation on the grandparent to finally resolve the violations and restore balance to the tree. Now, let's insert the node with the value 4 into the tree. This insertion again violates the red-red property, and since the color of the uncle node is red, we only need to recolor the parent and uncle to black, while changing the grandparent's color to red. After that, we will move upwards in the tree to check for any further violations. Now, let's insert the node with the value 20. In this case, the parent node is black, which means there are no violations of the red-black tree properties. Therefore, no further action is needed, and the tree remains balanced. Lastly, let's insert the node with the value 16. This insertion violates the red-red property. Here, the parent is the right child of the grandparent. When this occurs, the operations mirror those we discussed earlier. If the uncle node is red, we follow the same process as before. We color both the parent and the uncle black, while changing the grandparent's color to red, and then move upwards. If the uncle is black, and the inserted node is the left child, we perform a right rotation on the parent, recolor the parent to black, and the grandparent to red, and then execute a left rotation on the grandparent to restore the properties of the red-black tree. Finally, we ensure that the root node remains black. In this case, we first need to perform a right rotation on the parent node. After that, we recolor the parent to black and the grandparent to red. Finally, we perform a left rotation on the grandparent to restore balance to the tree. Now, let's look at the code for inserting elements into the red-black tree. First, we define the insert function, which takes the data to be inserted as an input parameter. In this function, we start by creating a new node with the given data and set its left and right children to the nil node. Next, we initialize two variables, parent, which will keep track of the parent of the new node, and current, which starts at the root. Next, we run a while loop until we reach a nil node, which helps us find the correct position for the new node in the tree. Inside the loop, we first update the parent to be the current node. Then, we check if the new node's data is less than the current node's data. If it is, we move to the left child. Otherwise, we move to the right child. Once the loop finishes, the new node's parent is set to the value of parent. If the parent is none, that means the tree was initially empty, so we set the new node as the root of the tree. Otherwise, we check if the new node's data is less than the parent's data. If it is, the new node becomes the left child of the parent. If not, it becomes the right child. Finally, we call the fixInsert method on the newly inserted node to correct any violations of the red-black tree properties. Next, let's see the code for the fixInsert method. This method is essentially the code implementation of the conditions we discussed earlier. We'll begin by defining the fixInsert function, which takes the newly inserted node as its input parameter. Inside this function, a while loop runs as long as the new node has a parent, and the parent's color is red, indicating a violation of the red-black tree properties. The first case we handle is when the parent of the node is the left child of the grandparent. In this case, we initialize the uncle node as the right child of the grandparent. If the uncle is also red, we recolor both the parent and uncle to black, and the grandparent to red. We then move up the tree by setting the grandparent as the new current node and continue the loop. However, if the uncle is black and the inserted node is a right child, we first make the new node, Z, the parent, and then perform a left rotation on the parent to adjust the shape of the tree. After this rotation, we recolor the parent to black, the grandparent to red, and finally perform a right rotation on the grandparent to correct the violation. If the parent is the right child of the grandparent, the process is symmetric. The uncle is now the left child of the grandparent. We apply similar logic. If the uncle is red, we recolor and move upward. If the uncle is black and the inserted node is a left child, we perform a right rotation, recolor, and then a left rotation on the grandparent. Lastly, after all the adjustments, we ensure that the root of the tree is always colored black, as required by the red-black tree properties. Now, before moving on to the delete operation, there are a few helper functions we need to review. The first one is the search function, which is used to find a specific element in the red-black tree. This function works recursively. It takes two parameters, the current node and the key we are searching for. If the current node is nil, or its data matches the key, we return that node. If the key is smaller than the current node's data, we move to the left child. Otherwise, we move to the right child. This process repeats until we find the node or reach a nil node. The next helper function is minimum, which is used to find the node with the minimum value. This is especially useful when deleting a node that has two children. First, we define the function minimum, which takes the starting node as its input. The function works by traversing the tree, continuously moving left, as the smallest value in a binary search tree is always found at the leftmost node. The loop continues until it reaches a node whose left child is nil, indicating the minimum node. Finally, we return this node. The next helper function is transplant. This function is used during deletion to replace one subtree with another. It essentially moves the subtree rooted at node V into the position of node U. First, if node U is the root, we set the root of the tree to V. If U is the left child of its parent, we update the parent's left child to V. Otherwise, we update the right child. Finally, we set the parent of node V to be the parent of node U. This function is crucial for handling node replacement in the tree when deleting or rearranging nodes. Just like insertion, deletion also has cases, starting with the case when the node that replaces the deleted node is black. This is the node that will replace the node being finally removed. If the replacing node is the left child of its parent, we need to examine the color of its sibling. If the sibling node is red, the first step is to recolor the sibling black and the parent red. Then, a left rotation is performed on the parent to balance the tree. After this, we check again with a different configuration. If the sibling node is black and both of its children are also black, we can recolor the sibling red and move upwards, setting the parent node as the new focus of the fix-up. If the sibling is black and the left child of the sibling is red while the right child is black, you first recolor the left child to black and the sibling to red, followed by a right rotation on the sibling. Now, if the right child of the sibling is red, the process is slightly different. In this case, we set the sibling's color to match its parent's color, then recolor the parent to black, and the right child to black as well, followed by a left rotation on the parent. Now, if the replacing node is the right child, the process is similar but mirrored. Instead of focusing on the left side, you look at the right side. If the sibling is red, recolor it to black and the parent to red, followed by a right rotation on the parent. If the sibling and both of its children are black, you simply recolor the sibling to red and move up the tree to the parent. If the sibling is black and its right child is red while the left child is black, you recolor the right child to black and the sibling to red, followed by a left rotation. Then, if the left child of the sibling is red, you set the sibling's color to its parent's color, make the parent black, and the left child to black as well, followed by a right rotation on the parent. Finally, ensure that the replacing node is always set to black. Now, let's see a few animated examples. In this tree, let's delete the node with the value 2. First, we'll delete the node as usual. The node that replaces it is the nil node, which is black. This triggers us to check for violations of the red-black tree properties, and we need to look at the sibling node and its color to decide what to do next. In this case, the sibling node is black, its left child is red, and its right child is a nil node which is black. This means we need to follow the rule where we recolor the left child to black, the sibling to red, and then perform a right rotation on the sibling node. Now, after the rotation, the configuration changes, and the right child of the sibling becomes red. In this situation, we'll change the sibling's color to match its parent's color, recolor the parent to black, and also recolor the right child of the sibling to black. Finally, we'll perform a left rotation on the parent node to complete the balancing of the red-black tree. Now let's delete the node with value 4. First, after finding it, we need to check for the minimum valued node in its right subtree, which is 5. We'll transplant the node with value 5 to the position of the node with value 4, effectively replacing it. Next, we establish the parent-child relationship between nodes 5 and 3. Since node 5 has now taken the place of node 4, we connect node 3 as the left child of node 5. Then, recolor node 5 to the color of node 4. At this point, node 4 is effectively removed from the tree, as no pointers lead to it. The only pointers that existed were from node 4 to its children, but these have now been replaced by node 5. Therefore, node 4 is completely disconnected from the tree. Now that the deletion has been completed, we need to fix the tree because the black height property is violated. The node that replaced the minimum valued node in the right subtree is a leaf node that is black. To restore the balance, we first check its sibling. The sibling is black, and both of its children are also black. In this case, we follow the red-black tree properties by recoloring the sibling red and moving up the tree. If you're unsure of how this works, refer back to the cases we've seen earlier during deletion fixes. As we move up the tree, we reach a red node. In this situation, we simply recolor this red node to black, which restores balance, and then we can terminate the process since no further adjustments are needed. Now, let's see the code for this. We'll start by defining the function delete that takes the target element as input, which is the value of the node we want to delete. First, we search for the node using the search function and store that into a variable z. If the node is nil, we stop the operation. We store the target node in a variable y, and we also keep the original color of the node in another variable. We then check if the left child of the target node is nil. If it is, we store the right child in a variable x, and then we transplant the target node with its right child. This process ensures that the target node is replaced by its right child, effectively removing the target node from the tree while maintaining the structure of the red-black tree. Similarly, if the right child of the target node is nil, we store the left child in the variable x, and then transplant the target node with its left child. Now, this x is the node that will replace the target node. This node is crucial because it will be the main focus during the rebalancing process and fixing any potential violations in the red-black tree's properties after the deletion. The cases for rebalancing the tree will be determined by this x. Otherwise, if the target node has two children, we will find the minimum node in the right subtree and store it in a variable y, while storing its color in another variable to track the original color. Then, we will store y's right child in a variable x. If the y's parent is the target node, then we will update the x's parent to y. Otherwise, we will transplant y with y's right child. After that, we will update y's right child to be z's right child and set y's right child's parent to y. This step ensures that y takes the place of z and maintains the correct parent-child relationships in the tree structure. After that, we transplant z with y. We then set y's left child to z's left child and update y's left child's parent to y. Finally, we change y's color to match z's color. This ensures that the color of the node remains the same as the removed one. Finally, if the original color that we've stored in the variable is black, we perform the fix-delete operation by taking x as input. This function is crucial for fixing any red-black tree violations that may have occurred due to the deletion. It goes through the specific cases we've discussed earlier, such as handling sibling colors and performing rotations, to ensure that the red-black tree properties are restored and the tree remains balanced. Now, let's go through the fix-delete function. This function takes x, the node that replaced the deleted node, as input, and it ensures that the red-black tree properties are restored. The function runs inside a while loop that continues as long as x is not the root and x is black. The loop stops when the node reaches the root or the issue is resolved. First, if x is the left child of its parent, we get the sibling node, w, which is the right child of the parent. If the sibling is red, we recolor the sibling to black, the parent to red, and perform a left rotation on the parent. This fixes the imbalance caused by the deletion, and we reassign w to the new sibling after the rotation. This case handles the situation when the sibling is red, ensuring the tree stays balanced. Next, if the sibling w and both of its children are black, we recolor the sibling to red and move upwards in the tree, setting x to its parent. This step helps maintain the black height property, pushing the issue up the tree and allowing the fix to continue until the imbalance is resolved or the root is reached. If the sibling is black and its left child is red, while the right child is black, we recolor the left child to black and the sibling to red. Then we perform a right rotation on the sibling to set up for further adjustments. After the rotation, we reassign w to the updated sibling node and continue fixing the tree. Next, if the right child of the sibling is red, we recolor the sibling to match the parent's color, recolor the parent to black, and recolor the sibling's right child to black. Then, we perform a left rotation on the parent to restore balance and set x to the root, which terminates the process, as the tree is now balanced. The function also has symmetric cases when x is the right child of its parent. In these cases, the logic mirrors the left child's behavior, but we check and adjust the left sibling instead of the right sibling. Finally, after all adjustments, the function ensures that X is recolored to black, ensuring that the red-black tree properties are maintained. Now, grasping all these coding concepts, cases, and red-black tree operations might feel a bit tough at first. So, my advice is to head over to the GitHub link I've provided, where you'll find the Python code with detailed comments to guide you through each step. You can try inserting and deleting nodes in the tree and work through the logic yourself to get a clearer understanding of how everything functions. Hands-on practice will really help reinforce these concepts and make everything much easier to grasp.